suppose that U is U1, U2 up to UN, and B is V1, V2, Vn. We're going to define U dot V. This is an inner product. Here's what you do. You just multiply the coordinates successively together and then add them up. And of course, at this point now you're probably saying, okay, Jim, now you're just making crap up. Physics. Right, what's this got to do with anything? How possibly be it used? Well, it actually is used. First of all, we've already been doing the dot product a certain extent. One can argue this. Here's a way to think about this. Let's think of it this way. This is just a matrix multiplication. It's U transpose times V. Let me kind of demonstrate why this is true. I know what V is. V is a stack. V1, V2, V. I know V. What is U transpose? Yes, my 4-year-old came over and knocked over the blocks, right? That's all that is. U1, U2, UN, right? Now, I don't know much, but this is a 1 by n matrix, and this is an n by 1 matrix. So if I multiply this correctly, what should my outcome be? It's a 1 by 1 matrix or a number, right? So there's only one row, only one column, so that's cool. And we multiply this like. So actually this dot product is a special case of matrix multiplication that we've been doing for some time now. Let me also point out as well. So everybody agree with that? Because if you transpose a number, it's just the number, right? So what's the point of this? Well, if you look at U PV, U dot V is U transpose V, or a little computation over there, and this is equal to its own transpose. Because this number should equal its own transpose. So here's kind of a cool thing. The order of the dot product doesn't matter. Now, by the way, this is very obvious from my first definition, right? But when you dot two vectors, does the order matter? No. Okay, so let me give you some properties of dot products, and we'll want these to be shared by inner products in general. So here's kind of our first theorem here. Let's let U, V, and W be vectors in Rn. Let lambda be just a number. So first property. We've already done this one. U dot V. V dot V. I mean, you take the two vectors, you multiply their sets of four sides, it doesn't matter what it is. Here's another one. I bet you can probably guess the outcome of this one. Let's go that one is. Exactly. It distributes out the way you hope it would. The next one, if you multiply the first vector by any scale, any lambda, and dot it with V, this is lambda, and U dot it with V. And of course, it doesn't matter if you put the lambda in the second. So any scale moves freely in and out of the components of the dot product. Okay. This one is actually rather important and is going to lead to what we do next. 4. What happens when you dot a vector with itself? Any observations you can make about it? Don't try to be too specific. Yeah, I think there's a simple option. Yes.
U squared.
You're on the right track. This turns out to be a number, right? What can you say about that number?
It's not.
Well, it could be 0, right? For example, one vector is. Can it be negative?
No.
This is greater than or equal to 0. And I'll show you ways it's pretty easy to see why it's true. And it's 0 if and only if the vector U is 0 vector. These are all easy to prove, but let me demonstrate why the fourth one is true. That's really kind of the interesting part of it. Let U equal U1, U2, UN. Then U dotted with U was just the square of all the components, right? Added up. And I don't know much. Well, when you add up a bunch of numbers that are, and of course, it's important that these are real, right? Not complex numbers. Otherwise, you could have I squared to -1. But here in the reals, if you square anything, it's greater than or equal to 0. No negatives allowed. So the dot product of any real vector itself, greater than or equal to 0, right? And what about the second statement? Well, the second statement, if U is 0, 0, 0, then U dot U is equal to 0. That's easy peasy lemon squeezy, right? What about the other way? Now suppose U dot U is 0. Well, U dot U is U1 squared, U squared, UN squared. Right? The only way for this to be 0 is if every one of those UIs is 0. If any of these is not 0, then one of these is positive and you can never recover from it. Everybody agree with that? So each UI squared is 0 because these are positive or 0. And so each UI equals 0. Hence, U is the vector 0, 0, 0 vector. This is actually rather important. This last thing, can somebody explain to me why this is important? The dot product itself is greater than or equal to 0, and it's only 0 if the vector was 0 in the first place. Okay, now you're talking about you can measure a length of a vector in an intelligent way. So now we can get a little geometry involved, right? Because we know that when you dot a vector with itself, it gives you a number that's positive. This allows you to measure some distances, right? And allows you to get various useful geometric things, triangles and so forth involved. And so we can actually define, and we will define a distance now. So we've been using this, you know, in some applications. So here we kind of make it with concrete. So suppose I have a vector in Rn, then the norm of B is generally we put like little double lines around it. It's sort of like norm is to vectors as absolute value is to numbers. We're basically measuring the size of this vector in a certain sense. Here, I'm give you some notation here to work off of. We'll find the norm of this vector and the square root of the vector dotted with itself. Since this thing is never negative, I've got no worries doing this, right? And of course, this is the square root of b1 squared plus b2 squared. bn squared. And basically what this does is this allows us to measure the size of the vector. So let me make a couple of notes here. Of course, the square, the norm, is also important, and it's just the vector dotted with itself before we get the square root. And let me also point out that then you want to tell me what that is? So what do you suppose happens to the norm scale of vector? So I've got some vector B, and I scale it by lambda. What's the relationship between the new norm and the old?
Lambda squared.
You're close, but it can't quite be lambda. Absolutely. Well, so there was a little bit of, let's make sure we know why that's true. So here's why that's true. So let B equal B1, B2 up to Bn. Then lambda B is lambda B1, lambda B2, lambda Bn. Right? So if you have this is the square root of lambda squared v1 squared plus lambda squared v2 squared plus lambda squared v n squared. Everybody agree with that? Square all those suckers, add them up. Now, everybody see that this has got a common factor of lambda in it that I can pull out. And so this is the square root of lambda squared times the square root of v1 squared plus v2 squared v(n) squared. Now, what's another name for this? What is this thing right here? This is the norm of V. And what's another name for this? This is the absolute value. Lambda. Any questions? Okay. Here's an example. This will show up later in the course with some various applications. First, I claim to put feedback to their face. Can somebody quickly verify for me why that's true? What's in it? Two of them, and they're linearly independent. That's one way to do it. Another way to do it is put them all in a matrix and take the determinant of that. This is simple enough where I can almost do that in my head. 6 minus 35, negative 29. Not zero, it's a basis, right? Everybody okay with that? Now, here's what I want you to do with this. Refine B so that basis elements are 1 unit long. Why would you care to do this? Because actually, what's going to happen when you do calculations, when you use bases for things like Fourier series, et cetera, you're doing calculations. If the basis elements are some crazy length, like 5 or 10 or the square root of 2, then in your computation, sometimes this gets things kind of tangled up and more complicated. If your bases are all 1 in a lot of computations, that makes it calculate. So I want to refine this so that I can take two basis elements, and since they're parallel to the original vectors, but I want them only 1 unit long. How would I do that? Well, here's a more general sweeping question to answer that we're going to use to answer this. Let V be not the zero vector. Then find a vector in direction of V that is a unit length. And by unit length, I mean 1. How do we do that? Yeah.
You can get the length of B and then divide B by that length.
Okay, that's what you want to do, because what you can do is if you multiply a vector by any non-zero vector, it's in the same direction. If you multiply by a negative, it turns it around, right? But if you multiply by a positive, and I do mean positive, not zero, number, it'll scale it, right? What I want to do is scale it to 0. Or I'm sorry, scale it to 1. So There you go. How about this? What did I do? I took my vector B. U and V are in the same direction because this is a positive number, right? So that's a scalar. Maybe I multiply by 5, divided by 7, whatever it took. So what we have now is that U is in the same direction as V. And I'm gonna verify for you that this is exactly 1 unit long. By the way, where did it come up that we needed V to be a non-zero vector?
Well, because it can't be on the bottom of
You are in Jim's world of pain if you have the zero vector here, right? That would stink, right? So that's one of the things I dig about math is because there's little things like that that if you pay attention, it kind of helps you along the path.
Plus, you can't make the zero vector any other length.
That's right. I mean, well, because you don't know what direction to go. That's the problem. So if you have this right here, is everybody comfortable with the fact that U and V are in the same direction? Because I've taken this and multiplied by scale. The only thing that perhaps I need to verify for you is the fact that this U is actually exactly 1 unit long. Well, let's look at U dot U, right? This is 1 over B dotted with right, okay with that? Well, remember, let's keep in mind, if I just for emphasis, I'll put these in parentheses. But these are vectors, but these norms here, they're just numbers, they're ordinary numbers. And one of our properties says I can jerk this all out in front, and in fact, what I get is 1 over the length of B squared. So I'll pull these both out and put them for safekeeping in front. And what do I get here? This is B dot B over the length of B squared, and this is the length of B squared over the length of B squared. So let's get back to our concrete example. I want to recalibrate my basis. So what is the length of the vector 1, 5? Should be the square root of 26. If I ever get it, 1 squared. And the length of the other vector, what was that? 7, 6 is the square root of 49 plus 36, which is the square root of 85. So my new basis, we'll call this basis prime, is 1 over radical 26, 5 over radical 26, 7 over radical 85, 6. And there you go. Got two sort of an improved basis, if you will. Same direction as the original, but now both of those things are going to one. Okay, any questions? All right. Let me, so we're going to get into a little bit of geometry, and I'm going to show you how to measure the angle between two vectors, which is kind of cool. First, let me give you a definition. And this is just kind of a notational thing. It's actually nothing that's really new. We can now define the distance between two vectors, and it's basically just the third side of the triangle. Definition. Let U and V be vectors and Rn, then the distance between U and V is so I will write DIST UV. This is what I mean, the distance between these. This is just the length of U minus V. By the way, does it matter whether it's U minus V or V minus U? No, because if I had done V minus U instead, that only differs by this by a -1. And when I suck that out with the absolute value, it doesn't make any difference. And that, my goodness, it should be that way, right? Because when I'm talking about a distance, I'm talking about a positive number, right? I'm not paying attention to direction. How far apart are me and you? We would say we're 8 feet apart. You would say we're 8 feet apart, right? And the distance, it shouldn't matter, which one you leave. Yes.
Yeah, so when I thought distance, I think if you've got two vectors like this, I would think this.
And that's what it is.
It is?
Yes. Yeah, and I'm glad you brought that up. Because that's what's coming next. If you look at, really good on our here. This is what I do. I'll do it U minus V. The distance, notice this is U, this is V, and let's see if I did this right. This is U minus V, so I didn't do that right. V plus this at the tail is that, right? And that's exactly what you're doing, because what this means is you're measuring the length and the difference of the vectors. So you're measuring the length of that orange vector. So that's exactly what you do. Does everybody see that? So the distance, basically you're measuring the distance between the heads of the vector. All right, that's what you're doing. This plus this is U, and the distance between U and V is just whatever this vector is, its magnitude, its norm. So, for example, let me give you. Well, so in particular, let's say that you have, I'll give you general formula. Why not? So if it's supposed to be is P1, P2, then the distance this is the norm of U minus V, which is the norm of the vector U1 minus P1, U2 minus P2, UN minus P1. Everybody agree with that? Oh, and I've got the tail end, which is the square root of U1 minus V1 squared plus U2 minus V2 squared plus UN minus VN squared. Everybody okay with it? You all have encountered this before. How many of you, in fact, you all probably have encountered this, maybe even back as far as high school. What happens in the case that n equals 2? What does this measure? Does this look familiar? This is the distance formula between 2 points in a plane. The two operative points here would be the heads of the vectors. But this is the distance formula between two. Those of you that had Calc 3, if I put a third one there, 3 of them would be the distance formula for 3 points in space, right? Or I'm sorry, between 2 points in space. Everybody okay with that? So this is just the distance formula, but now we can do it in any dimension we want. Everybody okay? This is, yeah, so this is basically, this is Pythagoras' theorem on anabolic steroids is essentially what this is here. Oh, and by the way, it's also the distance, it's the distance between 2 points on a line too. Because if you're down to 1, that's the square root of u1 minus v1 squared, which is the absolute value of u minus, right? So this all comes together. It ties the room together nicely. Okay. Any questions? Okay, so I'm going to do a couple of fun things here. The first question is, let me ask you this question. Would everybody agree that no matter what dimension of space you're in, if I give you just 2 vectors, there's a plane somewhere that they sit in, right? Even if it's a 5-dimensional vector, there's a 2-dimensional plane somewhere in 5-dimensional space that sits. So let me give you a question. 1, 0, 4, 2, and 7, minus 2, 6, 3, 10, and question. Are those 2 vectors perpendicular? If not, what angle do they sit at? Huh. So when are 2 vectors in Rn perpendicular? Perpendicular, you guys know what that means, right? Sits at 90-degree angle. You want to act smarter than your counterparts at USC, use the word orthogonal. That's perpendicular for people that have 3 digits in their IQ. And how about, and that's for me, which has less, how about just perpendicular? If I use that symbol, that's what I mean. When are 2 vectors perpendicular?
Product is 0.
That's what it's going to turn out. So let's see why that's true. So let me point out that if I have 2 vectors here, we'll call it U B, and we will call this one it doesn't matter, U minus 2. My question is when are U and B perpendicular? Well, U and B are perpendicular. Well, can anybody tell me what's a good way to do this? Think about Pythagoras' theorem. What is the relate? What happens if U and B sit at right angles? Don't you have a formula about the square of this and the square of this should be the square of that? So let's take that for what it's worth here. Yeah, the length of U squared plus the length of V squared is equal to the length of U minus V. Everybody okay with it? So if these are if these sit at right angles, then you have to have Pythagoras, all right? Let's take this apart in terms of dot products. This is u dot u. Plus v dot v is u minus v dotted with u minus v. Right, okay? You FOIL this out using our dot product stuff, and this is u dot v. Sorry, u dot u. Minus u dot v minus u dot v. Right, this one is u dot v, and this one's v dot u, but it doesn't matter what order, so I'll say two u dot v's. Everybody okay with that? And in the final dot, these cancel, and this is v dot. So I've got this equals this. And notice there's a lot of similar stuff on both sides, right? The u dot u, v dot v drop out. Everybody agree with that? So I get 0 is minus 2 u dot v, or u dot v equals 0. And in fact, it's an if and only if. V dot u equals 0 if and only if u and v are orthogonal. Okay, any questions? Any questions? So, look how easy this is now. Notice this is negative 26 plus 0 plus 12 plus 18 minus 4, and this comes to 30 minus 30 is 0. So these two are actually not at all clear from looking at it, is it? Right, but these two, wherever they sit in five-dimensional space, sit at right angles to each other. Any questions? Yes.
Can you also check if they're linearly independent? See if they're.
That's a good observation. It turns out that if they sit at right angles to each other, they have to.
Right.
Right.
Can they be linearly dependent if they aren't?
Sure. Think of two vectors in the plane that look like that. I mean, I can't stretch my fingers enough, but it really hurt. These are not at right angles, but they're certainly in linearly. So let's take this up a notch. In fact, let's go a little bit further here. And I'm going to give you something more general than this theorem about the dot product. This thing about the dot products being 0. So let's go a step further. If the two angles or if the two vectors are not at right angles, we can actually go further and measure the angle between them in the following sense. Suppose you have two vectors like this, right? And from my picture, it looks like they're not perpendicular. So what happens? What can I figure out? Well, let me point out that we have a triangle here that I'm going to try to replicate. And this triangle, the lengths of the sides are everybody agree those three lengths of the three sides. Now, you never thought the trigonometry would pay off, but here it does. Does anybody remember the law of cosines? Well, does anybody know that there is this thing called the law of cosines? People make YouTube videos about it and so forth. Well, so here's what the law of cosines says. It says, actually, I'll draw it here. I'm trying it here. The law of cosines is c squared is a squared plus b squared minus 2ab between them. And notice if the angle is 90 degrees, this drops out and you get Pythagoras theorem, right? So I'm going to do that here. U minus b squared is a squared, so that's length of u squared plus b squared, length of b squared, minus 2 length of u, length of b, cosine theta. But theta's the angle between. That's just the law of cosines, right? Let's take this apart like we did before. This is u minus b, dotted with u minus b, equals and this piece right here is equal to length of u squared plus length of b squared minus 2 u dot b. This is the same computation that we did before, right? When I dot out this, I get this. Now, and what I get is minus 2 length of u, length of b, cosine theta is equal to minus 2 u dot b. So I get this equation. U dot b is equal to length of u, length of b, cosine theta, or by the way, this is really cool because you can just take two random vectors in 10-dimensional space and make the angle between them, just like that. As long as neither one of them is zero vector. And the dot product tells you, just by itself tells you a lot. That numerator is always positive. If the dot product is 0, they sit at 90-degree angles. If the dot product is positive, they're acute. And if the dot product is negative, it's an angle that's more than 90 degrees, which is kind of cool. Yes.
Could you deal with the inverse tangent? Did you have U and B?
Yeah, but what if those are 5 vectors? How are you gonna figure out the inverse tangent there? So yes, you can always reduce it to trigonometry, but you would have to do a coordinate change to get it. The dot product allows you to do that, skipping over that kind of thing. They're turning into the right coordinates so you can figure out, you know, the inverse tangents and stuff. Okay, let me kind of give you one last sort of concept here. Last 5 minutes we got. Okay, this is another important thing about it. Suppose I have some vector in Rn. This is just some fixed vector. I'm just gonna use this as my tool all the time. I want to look at every vector in n-dimensional spaces perpendicular to that vector. This W is called, W is a subspace. What do you need for a subspace? Remind me?
Zero.
You need the sum, you need the zero vector. Okay, well, notice that B dotted with the zero vector is 0. So yes, zero vector is in W. Right? What else do you need? Right, you need it to be closed under multiplication. So if, or I'm sorry, under addition, W1, W2 are in W, then B dotted with W1 plus W2 is B dotted W1 plus B dotted W2, which is 0 plus 0. So W1 plus W2 is in W. And finally, you need it to be closed under scalar multiplication. And so notice if B dot W is 0, so is B dot lambda. So W is a substance. And we're going to look carefully at these subspaces coming up. Let me point out to you, more generally, if B in Rn is a subspace, then this is a new collection of vectors that I call the orthogonal complement. And sometimes we just call this V perp. It's everything's perpendicular, everything is V. This is the set of vectors X in Rn, such that X is perpendicular to V for all vectors. Little b, yeah. So the orthogonal complement of a vector space V is just all the vectors that are perpendicular to every vector in that space. So for example, if your vector space here in 3 space is just the XY plane, what's the set of vectors that's perpendicular to every vector here? It's this line, right? It's a set of all vectors here. They're perpendicular to all of them. I'll leave you with an exercise to cogitate. So see if you can show this. If A you have an n by n matrix, then you can show this. The row space of A what's the set of vectors that is perpendicular to everything in the row space of A? You've done this before. And in fact, if you look back at how you constructed the null space, looking back on it now, what you're doing is you're making a dot product. So verify this, that the row space, everything that's perpendicular to everything in the row space is in fact exactly the null space. And the column space of A, anybody want to guess at that one? I think you're onto it. It's the null space, not of A, but of the transpose of A. So see if you can sort through that. It sounds like something might be coming up. Any questions? All right, y'all have a great weekend and we'll see you on Monday.